So the next speaker is Kinneret Keren from the Technion Institute. Dynamics of Actomyosin Networks with rapid turnover.
First of mine, Jean-François, thanks for inviting me. It's been really a wonderful meeting. So I'm going to talk about dynamics of Actomyosin Network with rapid turnover. So I'll be focusing on contracting Actomyosin networks, which, as we saw in these 2 days, drive movement both on the single cell level and on tissue, like you can see in this motile keratocyte or in these cells that are confined, as well as in tissue scale where you have pulsatile, for example, pulsatile contractions during gastrulations, which drive the movement. And if you look at the spatiotemporal patterns in these networks, you can see various types of behavior. So you can see steady flow, like in these motile keratocytes. You can see periodic variation, like you see it in this traveling waves here. There are examples with one-shot contraction, where, for example, in this starfish oocyte, the network contracts and brings the chromosomes in a single contraction event. And then there are examples of pulsatile contraction, for example, here in the cortex of the C. elegans. And the focus of my talk will be looking at how the dynamic interplay between the mechanics, the force generation, which depends on the structure, turnover in the system, as well as the geometry of the system, leads to these diverse behaviors. So the approach we're taking is using a reconstituted system, which is built on xenopus cell extracts encapsulated in water and oil droplets. So the nice thing about the xenopus extract is that they bring the rapid turnover of the actin, unlike many of the in vitro systems which were done with actin filaments that don't turn over rapidly. Here we have rapid turnover, we have the myosin activity, and we can control the geometry by the confinement in the droplets. And we've worked for quite a few years in this system. We looked at the cortices, where you put an actin nucleated factor on the interface and you can reconstitute cortical actin networks that are capable of breaking symmetry. But today I'll be focused on bulk actin networks. So these are networks where the actin nucleation is basically in the bulk, and you get these networks that are three-dimensional bulk actin networks. So when you encapsulate these extracts in a water and oil droplet, basically this is what you see. So you have this, let me stop. Sorry. So basically what you see is, so this is basically just extract with Lifac to label the actin, and what you see are these continuous fluxes of actin towards the middle. And I should just note that this, we take the droplets and we squish them into a pancake geometry, and what you're looking here is this mid-plane of the network. And what you have is this steady state where you have continuous network flux inward, the network turns over, so there's the components break apart, and you have diffusive flux that balances. And this can go on for hours. You can notice this aggregate in the center. This is actually a boundary condition defined by the system. So these crude extracts contain particulates, which the network, like a fishnet, basically collects them all to the center, and you have this boundary condition, nucleus-like center in these aggregate. So we can quantitatively measure the density and the velocity of the actin networks here. And this is already a few years ago. We realized that what you see is that, so the density profile changes. You have highest density towards the center and goes down towards the periphery. What was interesting is if you look at the flow patterns, and you have this inward radial flow pattern, and it looks rather linear. So the velocity actually increases linearly with distance. And this actually implies that the contraction is homogeneous. So basically, whether you're at very low densities or at high density, the system contracts homogeneously. And this is so you get basically a density-independent contraction, which is not obvious because you'd expect both the forces generating the contraction and the resistance to be dependent on the actin density. And this density-independent contraction is actually rather general, so we can play around by changing, by adding components of the actin machinery to these extracts. So, for example, if we add a branch nucleator promoting factor ACT-A, or we enhance this assembly by adding choronin, cofilin, and AIP1, we can see that we still get these flows. The contraction rate changes in these with these different conditions, but we still get pretty much this linear contraction pattern. And what this means is under a variety of conditions, basically the driving force for contraction, the myosin-generated forces, and the resistance for contraction, which is primarily the viscosity of the network, scale with each other, leading to this density-independent contraction. Now, what we notice is when we take these system, we can get this continuous contraction that I just described earlier, but we can also get periodic global contraction that is periodic, as you can see here. And this turns out to be size dependent. So if we look at a bunch of droplets, what we see is in smaller droplets, we see this continuous contraction. And when we go to larger droplets, we see these waves, these periodic, concentric periodic contraction rate. And there's a pretty well-defined transition length between these, this continuous contraction and these wavy contractions. So this is just plotting the pattern that we see as a function of the size of the droplets. So if we look at these periodic contractions, so here you can see the density pattern and the velocity pattern, and here you can see chymographs on a radial cross-section, and you can see this is really nicely periodic. You see these periodic patterns both in the density and in the velocity of the network. And I should note that these periodic contractions have actually been observed. So ever since people started looking at extract systems, they noticed that there are these waves of periodic contraction, and these actually happen on macroscopic scale. So if you take a tube of extract, you see this global contraction wave on a tube scales, and these were interpreted as cycles of gelation and contraction. More recently, in a system very similar to ours, this group showed that you get these contraction ring-like structures, which they interpreted as being basically a contractile ring that assembles near the interface and contracts inward. So if you look at we can see actually if we look at droplets that are where the contraction center is asymmetrically localized, we can see that you can see both types of behaviors within the same droplet. So here you can see on the side that's closer to the interface, you see continuous contraction. On the side that's further away from the interface, you see these periodic waves. This is nice because it tells us that these wavy patterns are not due to some modulation or some issues related to surface to volume ratio, but actually are directly related to the distance between the contraction center and the boundary of the system. And also it tells us that when you think of these systems, we have to consider coexistence of regions with different contractile behavior. So again, we can change the properties of the system by adding different factors to the extract. And what you see here is that this pattern where you have continuous contraction in small droplets and periodic contraction in large droplets is quite generic. So by changing the condition, we can change the periodicity of the waves, we can change the transition lengths, but we see generically that you have continuous contraction in small droplets and wavy contraction in large droplets. What we see is that this transition lengths actually depend on the contraction rate. So changing these conditions, adding capping protein or adding different types of nucleators, the contraction rate actually decreases going from here to here. So we have decreasing contraction rate, and this comes along with increasing transition length. So the faster the contraction, we see transition in smaller droplets, and you see that the periodicity actually doesn't depend in a simple way on the contraction rate. Interestingly, if we look at these extracts, they're actually complex mixtures, and they can change over time. So if we image the same droplet over half an hour here, we can actually see the same droplet transition from continuous contraction to waves. And what's nice about it is that you can actually see how this transition happens. So initially, you see it breaking into these arches, and then they're synchronized, and then you see these very clear periodic patterns in the images. Occasionally, we also see these spiral patterns develop, so the same wavy patterns, but now in these spirals. And this appears to be the same type of wavy behavior, but broken angular symmetry. But this seems to be spontaneous, so we see with equal proportional spirals going clockwise and spirals going anti-clockwise. So you can see here the velocity patterns in a longer angular chymograph, and you see the lines going one way or another way in both orientations. Okay, so we want to understand what determines these different spatial pattern contraction patterns that we see, and in particular, why this depends on the size of the system and the contraction rate in the system. And to that, we turn to modeling this disordered networks of actin. So if you just have actin and cross-linkers, then this network these systems can undergo a percolation transition. So basically, if you have low connectivity, so this depends both on density of the actin filaments and density of the cross-linkers, these will be just unconnected pieces. If you increase the density or the amount of cross-linkers, you get to a percolation transition where the system becomes connected. And if you increase it even more, you undergo this rigidity transition and becomes rigid. Now, if you add activity to the system, so this has been studied by many groups over the last few decades. These are images from work from Heisha Cohendricks and Fred McIntosh. You can describe the system quite nicely as, with this state diagram, which is a function of the activity. So this is the motor activity and the connectivity as before. And basically, again, you have this unconnected state here where the system is broken apart and it's not connected. If you increase connectivity, you go into this connected phase. And now if you increase activity beyond some threshold, the system starts contracting, and you have global contraction. And then if you increase activity even more, you break into this local contraction. Now here you're thinking of the state diagram of the system, thinking of it as a homogeneous system which exhibits one of these states. But now, if we think of the system with turnover, and we have these continuous advections, you actually have to think about the flow and how the flow and turnover influences the density. And in particular, as you saw, the system becomes inhomogeneous. So there are different densities. So now, rather than thinking of the system as being in a state, we have to think of the system as spanning different states. So there will be coexistence of different local states in the system. So if you think of this state diagram I showed you earlier, now rather than thinking of it as characterizing the system, we can think about it characterizing locally the condition of the system. And we'll be dealing with these three different regimes: the gas regime, where the system is unconnected; the connected regime, where the system behaves like a viscous fluid; and then this contracting regime, where the system behaves as an active fluid. Here I'm taking just one active regime. Locally, the system is contracting or not. Actually, the local contraction will emerge when we consider the system, the spatial distribution of the system. And just to simplify things, rather than taking this two-dimensional state diagram, we'll think of it just as a function of density as a single parameter. So if you think of a system as the density is changing, so if the density is changing, probably both the motor activity are changing and the connectivity is increasing. So basically, as a function of density, you can think of the system spanning a line or a curve in this state diagram. And then in different regions of the system, we'll have the different phases. The gas phase, again, taking it basically as a no viscosity, no activity. The viscous fluid phase, intermediate region, where the network is connected, so it has viscosity, but it's not contracting, so we take the contractility to be 0. And then the active fluid state, where the network is both viscous and contracting. And now, in collaboration with Alex Mogilner's group, who's also here, you can describe this using a hydrodynamic theory. So as we've seen many times over the last couple of days, we have a mass conservation equation and a force balance equation. The mass conservation equation includes the advection that arises in the system and the turnover. And again, we're mapping the density field and the velocity field. And then the force balance we're incorporating, so we have the activity, the active stress to the myosin network, the viscoelastic stress, which we approximate as just a viscous stress. And the external forces in this case are the interaction with the fluid, which are rather negligible, so we neglect them. And now we incorporate this coexistence of states by saying that these parameters, the active stress and the viscosity, depend on the density according to these phases that I just showed you. And we incorporate the boundary conditions. So we're taking this pancake geometry, assuming spherical symmetry. At the center, we have zero flow. At the boundary, we have stress-free boundary condition. And there's another important boundary condition. There's actually a free edge between the gas phase and the network. And we incorporate some edge growth velocity to which physically would correspond to assembly at the edge of this network on top of the flow of the network. And now if you take this model with these boundary condition, you can get this state diagram now for the global behavior of the system. And you can see that the system will exhibit continuous flow in parts of the phase diagram, smaller sizes, smaller contraction rate, but periodic behavior in larger droplets or larger contraction rate. So in the in this regime, the system will stabilize. So you will start with whatever initial conditions you want, and the system will stabilize with this region of contracting. So this is showing you chymographs, showing you the density and the velocity as a function of distance from the inside to the outside. In this regime, the system will stabilize on a steady state. In the periodic regime, you're not able to stabilize a steady state, and what you will get is these periodic waves of contraction where you dynamically, these boundaries between these different regions change dynamically in this periodic fashion to lead to the waves. And the intuition here is rather simple. So if you think of the network, at the edge of the network, so this is the edge between the network that is connected and the gaseous phase. In this regime, where the size is small enough and the contraction is small enough, the advection, the movement of the network can be balanced by new assembly, and you can stabilize a boundary. In this regime, advection becomes too large. So this can become too large because the system is doing this telescopic contraction and the system size is becoming large, or because the contraction rate is becoming large. In any case, advections become too fast, and then you cannot keep up with the assembly, and what you have is a receding front that leads to this periodic modulation and these waves. Going back to these spirals, so I showed you that in this regime, in this periodic regime, we have this oscillator. Now, if you think of a true two-dimensional system, what I did before was essentially 1D. If we think of a two-dimensional system, then we have to think of these as coupled oscillators. The concentric waves are basically when all these oscillators are synchronized, but another solution can be a gradual phase shift along this system. And you can see here nicely a transition where we observe a transition between waves and spirals. So you can see here, this is again the angular density chimograph. You can see here a wave where the phase is synchronized across the angular distribution. And then it kind of jumps to this spiral and jumping from this synchronized to this gradual phase shift. If we look at this model actually at high contractility, you can look at this instability in the continuous model, but it's actually nicer to look at it in a discrete model. And what you can see is that if you use the same type of models with these three phases and you increase contractility, you can go from this continuous regime to the wave regime to irregular contraction to the formation of clusters just by changing the contraction rate, so effectively increasing the contraction rate. And indeed, if we take our system and we increase, in this case, capping protein, you see the transition from this steady-state global contraction to this periodic global contraction. And if you increase it even high, the system breaks into local clusters. So to summarize, I've shown you that we have this system of extracts encapsulated in cell-sized droplet. It's a nice system because we have the actomyosin physiological high turnover rates with myosin activity, and we can control the geometry. Obviously, these networks with rapid turnover are relevant for what's happening in living cells because typically cells will have rapid turnover. What I showed you is that it's important to, when we think of the system with turnover and we have advection, you actually have to think of the system as a coexistence of different local mechanical states rather than a state of the whole system. And then when you take this into account, you see that the solutions that you get, the spatiotemporal dynamics that you get, are actually dependent on the geometry. So we have this very clear size-dependent transition from continuous contraction to periodic contraction. And in terms of physics, it's a nice extension to what people have done with percolation models. So people have looked extensively at percolation models. Now we have an active version of that where you have to consider not only percolation of a connected network, but you also have to incorporate advection. And this gives a dynamic version of this percolation problem. And it's very rich because the force generation is dependent on the structure, which depends on the turnover and advection in the system. Okay. So finally, I'd like to thank my coworkers on this work. So this droplet system was initially developed by Inas Abu-Shah when she was a graduate student in my lab, and then the current work I showed you, the steady-state dynamics were characterized by Maya, and the waves were characterized by Niv and Ashwini. And we're also enjoying a very long collaboration with Alex McGillner and Maria from his group doing the theory part. Thanks.